This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So there seems to be a problem with the audio. I'm just calling the support. Hello, I'm in Elizabeth Murdoch Theatre, and the audio is not working again. That was the same problem as last week. Yeah, this morning, the mic, I don't hear anything in the room. Yeah, I'm trying both of them. I tried everything, okay? Yeah, thank you. Tansu Alpçıkan. No, you cannot. Come here. I'm in the middle of class, okay? Sorry? GO6, yeah. Yep. All right. Do you hear me? The mic is working?
No.
Is the mic working or?
No.
I have a good voice. I know that. I don't know whether I think it's just yeah, it's not working. So I don't know whether it's recording or not. So I think I should do the announcements a bit later. But you know there's a mid-semester test next week, right? Thursday. And I will send I keep there is a syllabus, right? It was in the LMS since the beginning of the semester. There is no syllabus tradition in this university, right? Not everyone posts what's going to. All the subjects, tentative plan is there, which workshop is there, etc. Some of you don't know, some of you know it. Good. This week we start the workshops on machine learning, so we are a bit behind. So today I'm going to complete the topic on optimization, and then start with machine learning next week as well. This is not a big deal because we will not have any workshops during the mid-semester week, which is next week. So you will do, then the week after, again, you will continue the machine learning workshop, the same workshop, and then the reports are due after the break. So you will have plenty of time to finish your report. So that I'm hoping that will, and then I'll be sure to make workshop 3 and 4 a bit shorter. I was given the feedback it's a bit too long in terms of number of tasks. So 3 and 4 will be a bit shorter, a bit more open-ended. So hopefully that will solve the issue. Any questions regarding that? I will send some emails regarding the mid-semester test, what to expect and so on. Questions? Concerns? No? All right. That's good. What else? As I said, some of the questions, like question 10, 8, I leave them as exercise questions. That doesn't mean exercise questions for mid-semester test. These questions are a bit more involved than the mid-semester test questions. So the mid-semester test questions will be simpler than those exercises. They are general exercise questions which help you go a little bit, get a better understanding of the topic by doing. They are good questions, but yeah, I don't have the time and I want to switch to machine learning. All right. Assuming that this is recording, I'm going to continue. Maybe it's recording, just the room audio is problematic. That's possible. Let's have quiet, please. Since you showed up here, have a nice, quiet, lecture. Thanks for that. So we were talking about constraint optimization. Today's topics are very important: duality and penalty methods. And I'm going to touch a little bit on multi-objective because of the penalty methods. First of all, we were talking about the Karish-Kuhn-Tucker conditions, right? That's something everybody knows in constraint optimization. It's a very important thing. And when you have just to recap, when you have the general formulation, this is the canonical form for convex optimization. So you minimize a convex function, and this is supposed to be a convex set, then it is a convex optimization problem. And here is the linearity constraints. And then it is customary to write the inequality constraints are less than or equal to 0, which you can convert any inequality to less than or equal to 0 easily, right? And then you write the Lagrangian, and then take the derivative of the Lagrangian with respect to the objective function, which gives you this. If you take the derivative of the Lagrangian with respect to the Lagrange multipliers, you get directly the constraints. So this is also part of the Kuhn-Tucker conditions. And then you write the complementary slackness condition, equation number 36, which for inequality constraints, which means either the Lagrange multiplier is positive, the constraint is active, which means it's an equality now, or therefore it's 0, multiplication is 0, or the constraint is inactive, it's strictly less than 0, but then the Lagrange multiplier is 0, therefore the product is 0. Right? We don't have this active inactive thing for the equality constraints because they have to be satisfied every time. Right? There is no flexibility there when you have an equality constraint. So, and we solved the special case when we don't have Lagrange multipliers because of regularity not satisfied. And then the second order necessary conditions follow from the previous discussion directly. And when you take the second derivatives, like this is the in this notation, this is the Hessian of the unconstrained objective function, and then these are the second derivatives, just like Hessian defined, of the constraints. And then when you add them up together with the Lagrange multipliers, you get this matrix. And the matrix, if the solution is a minimum, then this needs to be positive semi-definite on the tangent subspace of the active constraints, or it becomes a sufficiency condition when it's positive definite. So think of it, this matrix L, a counterpart of the Hessian for the constraint case, right? And the most general constraint case. We have seen the counterpart for the linear equality constraint case. Now this is the most general case where you have both equality and inequality constraints. And then just like the second derivative being positive, right, it goes back to that in the scalar case if you want the intuition. Now we have the multivariate case for the most general constraints, and then the sufficiency is then positive definite matrix on the tangent subspace. What is the tangent subspace, you may ask? It is at the x star, at the minimum. Here is, if it's the constraints were a sphere, then the tangent subspace in 3 dimensions would be a kind of a plane, right? And then here what we have is, as you can see, if I'm on that plane, so the derivative with respect to the constraint and with respect to the equality constraints, we have seen this before. Now we also add the active inequality constraints to the equality constraints. The normals to the gradients of the active inequality constraints serve as the normal of the tangent plane, right? And when we define the tangent plane with a normal, as you have seen in the notes. So that would be then J is the set of active constraints. This would be the tangent subspace, and this L needs to be then positive semi-definite, and the sufficiency condition positive definite at the tangent subspace that is defined at x star. So that's the, as I say, it's a generalization from the simple case of second derivative being positive to all the way here. This is the most general case. So there is a nice supporting hyperplane interpretation of KKT conditions, and I thought this is a problem that's worth knowing. There is actually a lot of deeper stuff that I'm skipping here about, supporting hyperplanes and then how the hyperplanes separate two convex sets. There are a lot of deep results that are not only for Euclidean spaces, but also infinite spaces, dimensional spaces, if you do infinite dimensional optimization, which we are not doing, obviously. So you can go much deeper mathematically into this, but I want to keep it simple. Consider a convex problem with no equality constraints like this, for example. This is the objective, these are my equality constraints. And it's a convex problem means these inequality constraints, no equality constraints. Inequality constraints, the intersection of these will be a convex set, obviously. And then we have a solution. What is a solution? It is the X star, but also lambda star. And that satisfies the KKT conditions. So we have then, these are the KKT conditions that we write. And what we want to show is, here this comes directly from the Lagrangian, right? And then this is the complementary slackness condition. Because this is an inequality constraint, the Lagrange multipliers have to be positive. And then these are the constraints themselves, Fi, actually, yeah. The notation is, this is from Boyd's notation. Boyd uses F0 for the objective and Fi, F1 to Fn for the constraints. So these are, you see the constraints are also part of the KKT conditions. This is a good example of, for this general case, here's how I write the KKT conditions, right? And what it wants us to show is this supporting hyperplane at the gradient of X star and then X minus X star. So let's solve this together and then I'll show you what it means. So we can actually go to the notes. So we have this, sorry about that, yep, we get that. Let's see. Maybe we can zoom in a bit more. No technician is coming, so I'm assuming, yeah, it's hopefully recording, otherwise it is what it is. I'm told that you shouldn't expect it to be recorded, it's an additional thing. So the university told me that university rules say, they told me you shouldn't expect the recording to be there. So that's what they told me. Okay, yeah, technician is here. Good. So just to, before blame me, then complain to the university. So we have this, yeah.
So is it just the microphones, or is it the whole thing?
I don't know. So suppose, X is feasible. We know that we have this already. Oh, I have a colorful pen here. Make it.
Reset that. They'll probably turn this off for about 30 seconds or so.
Okay. So there is now debugging of the system. So the recording will stop or will it continue?
It'll start after it restarts.
Okay, then I will wait. We can maybe chit-chat during this time. So here are the constraints, right? All this stuff, anything not clear to you? And at the X star, so it's working? But the touch panel is not. Do we really need that much complexity? That's the other thing, of course. Maybe it's not a surprise. A good engineering principle is keeping it simple, right? You know that. I mean, the more complex you make the system, the more trouble it will create for you. That's an important life engineering principle. I'm seeing like 10 pieces of equipment there. Who knows which one is throwing it? So is it working now? Yeah. I cannot adjust the volume. Or is it too much to ask?
The microphone is actually just got a room.
Yeah.
Yeah, and that one.
Yeah. Really, half an hour is gone. Okay. All right.
Okay.
Thank you. Thank you very much. Okay, I don't know how much it was recorded and how much it wasn't recorded, so it's sorry about that. All right, so let's solve this question 7, and then see how the life goes afterwards. All right. So the constraints are convex. That means we know that they are less than or equal to 0. So I can write this. So I can write it. Let's use nice black pen. So, and then this is too thick. So make it a bit. Yep. So 0 less than or equal to fi at x star, just like fix less than or equal to 0, right? And then it is above the line at x star. So I can write the tangent at x star, and that would be fi x star, right? This is the ith one. I can write for any ith one plus the, just like writing a line, but in multi-dimensional case, then this would be then x minus x star. You can check how to write a line in a multi-dimensional. So this is directly from convexity, right? And then we know we know also this, lambda I star greater than or equal to 0. Very good. So we just plug things inside each other. Actually, this is not a terribly difficult question. So we know that this right-hand side is less than or equal to 0. So we can write it this way. So let me write it here. 0 greater than or equal to 0. And then we can write it as a sum over I over all the constraints, right? Each of them is less than or equal to 0. Then lambda I star times these, fi x star plus grad fi x star x minus x star, right? These are vectors. Gradient is a vector as well. And then there is a multiplication here, so this is a dot product. Therefore, transpose this, so it's a scalar. So these are all, it's important to note that these are greater than or equal to 0. These are less than or equal to 0. So their multiplication will be less than or equal to 0. Then you sum up a bunch of negative numbers. It's still a negative number, so, or less than or equal to 0. All of them are with equalities possibility. So this still holds, right? And then we can rearrange the terms. So this is equal to then, we can plug them together. So this is lambda fi x star plus the second part will be then I equals 1 to m, lambda I star, this. So we are slowly coming to the what we want to show, right? The goal is this. This is the goal. So x star, again, transpose x minus x star. Okay, so that is essentially the line, as I was saying, the gradient line in the multidimensional space. Now, from complementary slackness, this is equal to 0. Notice that, once we know it, this is star. So that goes out of the way. And then we also have the last KKT condition, which is this, right? So note that we have this f0 x star plus sum of the I equals 1 to m, lambda I star gradient fi x star, right? So actually, you see this sum, I can write it as minus gradient f0. So this is actually minus gradient f0 x star transpose times x and minus x star remains the same. So then that will be then 0 greater than equal to, right? But then that's all what we wanted to show. So we got the result. So what you see is KKT conditions give you a supporting hyperplane, right? Because the line in n-dimensional becomes a hyperplane. Plane becomes, the shapes in higher dimensions don't have the same names anymore. So the tangent hyperplane. I showed it as a line here for two-dimensional space. In n dimensions, it will be a hyperplane of n minus 1 dimension. So in 3 dimensions, it's 2D. In 2 dimensions, it's 1D, right? 4 dimensions, it will be 3D. One less dimension will be the supporting hyperplane. So this actually then, so this is minus. So we got the result. The result is actually, let me be clearer. So if we multiply both sides with a minus, then it will be this, right? Dot. This will be then the dot product greater than or equal to 0. Right? So that will be a supporting hyperplane at the x star, right? So that is the supporting hyperplane interpretation of KKT conditions. Directly from the KKT conditions, we get a supporting hyperplane, and that's kind of interesting again because it also shows that the KKT conditions give you the solution is at the boundary. It's inner, either inside or at the boundary. If it's inside, then it is simple. But then, if it's at the boundary of the active constraints for the inequality, you get this supporting hyperplane. As I say, there is a lot of interpretation and more story to that. I had to remove that. I was going to put it to the slides, but because of time constraints, I want to keep it a bit simpler and go to the, finish the topic. So at least you have a basic understanding of the story. But you can go deeper into Boyd's book and read more about this whole geometric interpretation of KKT conditions. There is a whole geometric story there that I'm kind of skipping. But for those who are more interested in optimization, I would recommend you to go do that. Another important topic in the remaining time is the sensitivity and duality. So these are also quite deep concepts and worth going over, but since this is your first optimization subject, again, it's sufficient to get a basic understanding. You don't have to learn all the deep interpretations. You can learn the basic machinery at least, which will be useful in life, hopefully, in the future as an engineer. So we have the classic family of problems, but now what we do is actually, we don't play with the objective function, but you see they are normally C and D are 0. Right? In the canonical form, you write them as 0, right? You can always bring them to the 0 form, but what we are going to do is we will take these zeros and then change them to variables, C and D, for example, and then that means I'm just changing little bit the constraints and try to figure out how these changing constraints affect my solution. That is a sensitivity analysis. How does the parameters affect the solution? The sensitivity in general is about that. And anything you solve, how will the variations in input parameters affect the output for any problem, also for optimization problems. So this is a nice visual I found on the web. So you have an objective function you try to maximize, right? So under this blue constraint, the maximum will be this, right? This top of the thing. Unconstrained, maybe it is this one, the peak, but constraint one is this. What happens when you move the blue line? It's all about that. So if blue plane in this three-dimensional picture, if you move it a little bit to the left, your solution will change. If you move it a little bit to the right, your solution will change, right? The constraint, active constraint, directly affects your solution. So it could be equality or inequality, but active. It has to be active, otherwise inactive constraints don't have an effect on the solution. So we are kind of investigating here the sensitivity with respect to changes in the constraints. And then algebraic way of, this is a pictorial representation to give intuition. Algebraic way is C and D. If we write some C and D here, when C and D is 0, we have the original problem. If we make C positive little bit and negative little bit, same way D negative little bit, positive little bit, of course for each of them, these are vectors, right? A lot of degree of freedom. Then we will see how X star changes with respect to those, right? And this theorem, sensitivity theorem, is about that. When you read it, there is a local solution X star. That's a regular point. We assume it's a nice solution. We have the Lagrange multipliers, which satisfy second order sufficiency conditions for a strict local minimum. So everything is nice, strictly convex. We have second order sufficient conditions that we discussed. And we assume that no active inequality constraints is degenerate. This is an additional assumption we need to make. What does this mean? It means that when we change these constraints like I described, the small variations do not violate the positivity of active inequality constraint multipliers. Multipliers of inequality constraint have to be positive, right, when they are active. So we are assuming that we make C and D are small changes with respect to 0. So they are still, we still get positive Lagrange multipliers as we should. Right? Otherwise, you may have degenerate situations as we discussed in that example. So, assuming everything is nice, long story short, what does it have? How does the solution change with respect to C? That's, you take the derivative. Sensitivity, if you can, is found by just taking the derivative with respect to the parameter you are changing. And what is the objective? F. And what am I doing? F of x CD, x that you find from CD, and then take the derivative with respect to C. And at 0, 0, when C and D are 0 at the original problem, this derivative is actually minus lambda. And the derivative with respect to D similarly is minus mu. And that's interesting. So the Lagrange multipliers tell me how the constraint affects the solution if I change the constraint a little bit. Right? That's the whole story. How does the solution depend on the changes in the constraints through the respective Lagrange multipliers? Okay? For each constraint, the respective specific Lagrange multiplier of that constraint at that original point tells you, okay, I changed a little bit, then Lagrange multiplier tells me how much it will affect the solution. So this is, of course, a first-order approximation, right? But because we are talking about small changes, that's the sensitivity analysis, then that's kind of sufficient. There is actually a deeper interpretation of this. So the sentence is, again, quantify, Lagrange multipliers, quantify the change in optimal value of the objective function due to the relaxation of constraints, which is the C and D. And then when I take the derivative with respect to those parameters, that's sensitivity analysis, right? Google sensitivity analysis, Wikipedia is just saying, take the derivative of the solution with respect to the parameter. In this case, parameters are CD. Hence, they are also called shadow prices in economics. There's an economic interpretation. Actually, if you think about it, the constraints are affect the problem, remember, through the Lagrangian, through the Lagrange multipliers. So the Lagrange multipliers tie the constraint to the problem. So if you have a constraint problem, the Lagrange multipliers are like the price you pay for that constraint. And in economics, they are literally the price you pay. Like you want to go to the market and you want to buy tomatoes. If there is a constraint on the amount of tomatoes, that constraint will increase the price of tomatoes. So there is that relationship. The economics is a longer story, but this graph also shows if there is no constraint, you get the maximum peak. The moment you have a constraint, right, that affects the solution. Therefore, if I make small changes in the constraint, obviously the Lagrange multiplier of that constraint dictates how the objective changes. Yeah, so that's the story with the sensitivity and shadow prices. And that pops up more and more in engineering as well, because sometimes in engineering you need to take into account the economics constraints when you do design. You don't do design anymore in the vacuum, right? In a modern engineering, you do designs under constraints that also come beyond engineering. So you cannot build the best system you can. That's an utopia. You usually build the best system you can under the constraints. I'm teaching the best subject I can under the constraints of the university, right? So no matter how much I jump up and down, I'm constrained that are, you know, imposed. So what can you do? So that's how life is. Duality. So this is also very important, and then it's not tied up to it's a bit kind of follows up that discussion, but it's a separate thing. So let's look at the case to make things a bit simpler, where we have inequality constraints. Only, let's skip the equality constraints for now. This is the canonical standard form, and then the problem. Let's assume that it doesn't even have to be convex. It can be any feasible problem. So this duality is a more general thing. But then assume that the set is convex, the constraint set, and we define this omega of z function as the minimum, inf or min, read the same if you don't know basic elementary analysis. You can replace it with min for my purpose. Minimum of f of x such that, such that g of x is less than or equal to z. So this is similar. So I'm parameterizing the constraint by z. When z equals 0, I'm at f star, right? Omega, value of omega will be then min f of x, g of x less than or equal to 0. That will be the solution of the problem. It will be f star. And when I change z plus or minus, I get a bunch of results, right? And then the sensitivity analysis will be then the first degree approximation around f star. So this is just the general, let's say, you can solve a family of problems for each z and then get this curve, right? There's nothing interesting here. All right, so that's the original problem. That's the primal problem, as we have been doing. Now, actually, I can take this problem and define a dual function. What do I do there? I take the original problem and take the minimum of the original problem, find the x star, and plug that x star back into the Lagrangian. So if I do that, if I write the Lagrangian, find the x star and plug it back in, I get a function of mu only, because I have been minimized with respect to x star, and just write the Lagrangian, take the minimum with respect to x star, I get now the Lagrangian where I get an x value fixed now, I plug it back in, so I get a function of, dual function of mu, right? And actually it turns out if this is, f is convex, this is concave on the region where it is finite. So then I get this mu function, and then I can actually take the maximum of this mu function with respect to phi function, I'm sorry. I get the phi function. So I take the Lagrangian, take the minimum of the Lagrangian with respect to x star, plug it back in, so I get a function of mu, which is phi of mu. Then this phi of mu is concave, and I can take the supremum of phi of mu with mu greater than or equal to 0. That also comes from the KKT, right? The Lagrange multipliers for inequality constraints have to be greater than or equal to 0. So I get this kind of the dual problem of the thing. And graphically, the dual problem may not give you, in general, may not give you the same result. So if you maximize this phi, maybe the phi star is less than it doesn't reach the minimum of the f. I'm kind of approaching it from the other direction here, so from the bottom up. So the original problem comes from here. I'm going from here, from when z equals 0, which is the original formulation. So third, then this brings us to the weak duality proposition. So if you do this, then phi star will be always less than or equal to f star. And there's a highest hyperplane interpretation. So this will be on the highest hyperplane that is underneath this omega z. And then the intersection of that with the z equals 0 will give you this. So the dual function then gives a lower bound on the optimal value f star. So there may be a duality gap. So if I solve the dual problem, I may not get the same result, right? So let's look at then, the question is, when do I get the same results? It would be good if I can solve the problem in a different way, right? We like different ways of solving problems. Maybe they make our life easier. So in the general case then, if I write the equality and inequality constraints, assume H is affine, F and G and theta are convex. These are convex functions. This is a convex set. Right? Everything is a nice convex optimization problem. The dual function is then, I define, as I say, in the general case, is the minimum with respect to x, f of x plus this, right? And then, as I say, I find the minimum and plug it in. Then phi becomes a function of only lambda and mu because I have kind of eliminated the x. And the maximum of, then it becomes actually, if f is convex and then everything is convex, the constraints, once I do it, the maximum of this becomes a concave function and has a maximum, and the maximum of this is just given by this solving the optimization problem. Sup is supremum, but you can replace with max if you want. Max phi over lambda and mu, and lambda can be anything, but mu has to be greater than or equal to 0, right? And f star is the min of this. So f star is the original problem's minimum. The weak duality theorem says phi star is less than or equal to f star. Yeah, that's when I come from the bottom, I might not need to reach to the same level. But if the everything is nice, H is regular, and everything is convex as it should be, if everything is convex, and if there is a condition, if there is a point for which all of the inequality constraints are less than or equal to 0. That means there is a point inside the inequality constraints. I will come to this again. If you satisfy this, that's actually good enough so that, this is not only less than or equal to, if this is satisfied, then you get the same result as the original problem. Moreover, when you solve the dual problem, the lambda and mu that you find are the Lagrange multipliers of the original problem. Okay, so essentially, to summarize, I minimize the if I minimize the original problem, right, primal problem, which we usually call it as the primal problem, I can find the f star as we have done until now. Then, actually, I have an option of defining the dual problem by defining this phi through the Lagrange multiplier and eliminating x, and make it a function of the Lagrange multipliers, and this is the inequality version, then mu will be greater than or equal to 0. So, and if the strong duality holds, the conditions, sufficient conditions hold, then maximizing phi gives you the same result as minimizing f, and then there is no duality gap. They are the same point. This is really nice because, as I say, you can take an original optimization problem, write the dual function, and turn it to a maximizing the dual function problem in terms of the Lagrange multipliers. Right? And sometimes it's easier to solve the dual problem than the original problem. Can you imagine when? Let me give you an example. So let's say I have an original problem. X is 100 dimensional. Okay? Maybe X is 1000 dimensional. And let's assume it's a constraint optimization problem. And let's say there is only one constraint. So then there will be only a scalar lambda or mu inequality constraint, right? So if I write the dual, first of all, in the primal problem, it's a 100 dimensional or 1000 dimensional optimization problem, right? When I give you to the computer, it will have a bit choke on it. But it has a single constraint. If I write the dual, of course, writing the dual, it takes a little bit of effort. we need to still eliminate x, but let's say I can do it analytically, and then the problem becomes just in terms of maximizing phi of mu and mu. But I said there's only one constraint, so it is a scalar optimization problem. Suddenly, instead of solving a 1,000-dimensional optimization problem, you're solving a scalar problem. Make sense? So it's much easier to do that. So that's why, and if the strong duality holds, you know that you will get the same result. Even if it doesn't hold, you may use it as a starting point, like if it's a very complicated problem. You know that the dual will give you some lower bound, and the lower bound may help you in your engineering design. So even then, it is not a bad thing. The question is then, when does this strong duality hold that when I solve the dual, I get the same result? You need to know that, so to be able to say, is it a lower bound, or am I really getting the same result as before? When the constraints are linear and the constraint set is polyhedral then, and with additional linear constraints, then you get the strong duality. Or if it's a linear program where f is linear and g and h are affine, then you get the strong duality. So all the linear programs, you write the dual function and solve the dual problem, you get the same result as the original problem. Or when the Slater's very famous Slater condition holds, which is the same condition as in the previous theorem, but I put it into the box. If the primal problem is convex, f and g are convex, and h is affine, as we have been discussing in the canonical format, h needs to be affine, that is linear, right? Linear plus constant. So this is important. And there is a y such that, so if in the set of constraints there is a point such that the point satisfies equalities, has to, obviously, and for that point, all of the inequality constraints are strictly less than 0. That means it's inside that polytope, right? There is a point that is inside the polytope for which it doesn't touch any of the polytope boundaries. It only satisfies the linear constraints, and g of y is strictly less than 0. So then that's called the Slater's condition. Then you know, okay, strong duality holds. If I solve the dual problem, I will get the same result. All right? Any questions or anything you would like me to repeat that's not clear? Let's do one example first, maybe. So question 8 is it takes a lot of time. You can do it at home. Instead of that, I'm going to do question 9. And the solution is already posted. So I recommend you to try to do question 8 also yourself. And then, you can cheat and look at the solution if you get stuck. And then discuss with me during the consultation hour as well. But let's do because it's the same idea, we can do it as well for the linear program that we see here. It's an LP, right? And 9, we will do, the machinery is the same. Steps are exact the same steps for solving that. So, I pressed the wrong button. Okay, very good. So, we have a linear program. Why is it called a linear program? Because everything is linear, right? Linear or affine. So we have the C transpose X, Gx less than X. This is actually, again, an element by element notation. So everything is less than or equal to H element by element. So this is a bit like, we can write it a bit like Gx. G is a matrix, X is a vector, and the ith row is less than or equal to hi for all I rows, right? That's what it means, if it's not obvious. And then ax equals b is ax equals b. So we can bring this to the canonical form, saying, gx ith row minus hi less than or equal to 0 for all I rows, and ax minus b equals 0, right? That's then the canonical form. And C transpose X will be then the constraints, and then minimize C transpose X. I can write it as Ci Xi, right? For the dimension of the X vector. So X is R to the N. So decision variable is minimized. You see, this is what I was saying. So minimize, you're supposed to read the mind of the question asker and know that it is minimizing X. So this should be better written as min x. I would like you to write always like this, please. Don't take shortcuts. Write what you are optimizing. Because you see, in primal, it's one way, the dual, the other way, the variables change, right? All right. So let's do this whole dual business. You haven't done this before. First step, we write the Lagrangian. Write the Lagrangian. Because the question says give the dual problem. We write the Lagrangian. Lagrangian is lambda x, Lx lambda mu. You can call Lagrangian whatever you want. Some books call it L, some books call it small l. We write it as simply gx minus h plus mu lambda transpose ax minus b. Let me write it as mu. The solution, okay, let me follow the solutions notation because otherwise I will have trouble and make typos. Okay, so what do we know? So we know that lambda is greater than or equal to 0. This is an element of R to the, I will be element of R. Can be positive or negative because this is the Lagrange multiplier associated with the equality constraints, can be positive or negative, but the Lagrange multipliers associated with the inequality constraints have to be greater than 0. How many constraints do I have? It depends on the dimension of the inequality constraints and dimension of the equality constraints, right? I have that many Lagrange multipliers, and then the dimension of G, the dimension of H dictates the lambda vector, and the dimension of the B dictates the mu vector. Nu vector, not mu. All right? I mean, you need to know how to Lagrangian. Now, I can actually put the terms together and write everything in terms of x. X minus then H lambda transpose, or it doesn't matter, it's a dot product, right? Minus mu transpose B. These are just dot products of two vectors, so you can write the transpose and it will be the same thing because they give a scalar. So this is minus. Good. So now, what do I need to do? This is a linear function of x, right? To find the dual function, the dual is defined as, let me be very mathematically incorrect and write it as min. Actually, it's not min, it's infimum. But if I minimize Lagrangian with respect to x, then I get a function of only lambda and nu, not mu, nu. All right? So, how do I do that? Actually, because it's linear, I can see it immediately. The function is L is linear in x. That means if the coefficient of x is positive or negative, I can choose x minus infinity or plus infinity, and I can minimize, right? So the g function is actually, first let's realize this, is minus infinity if the coefficient is not 0. If it's plus 1, I can choose minus infinity. If it's minus 1, I can choose plus infinity as x, minimize it to minus infinity, right? That's why it's infimum, not minimum. Only when the constraint is 0, then I get the remaining things as the value. So the L is actually minus H, or I mean it keeps changing the notation here. Let's write it as lambda T H. Let me write it this way as well. And then minus mu TB. When does this happen? When this is 0. If C transpose plus lambda G plus mu transpose A equals 0. Else, I get minus infinity. You're with me? Right? Now I defined the dual function. Actually, in this case, it was easy. Sometimes this is quadratic. Then you just take the derivative with respect to 0. Then you find the x, plug the x back in. You get rid of the x and get a function of the Lagrange multipliers. So this is the dual function. Right? We are, of course, interested in the dual function when it is not minus infinite. So then the dual problem becomes immediately we get the dual problem. What is the dual problem? I need to maximize the dual function. So I maximize over these the dual function, which is minus lambda t h minus mu t b, right? Or which is equal to lambda dot h minus lambda dot h minus mu dot b. These are dot products of the two vectors. When is this valid? Only I need to impose the condition C transpose times plus lambda G transpose lambda plus A transpose mu equals 0. Maximize this. Only this makes sense. Maximizing this makes sense only when this is equal to 0. Otherwise, it's minus infinity. Maximizing doesn't make sense, right? And we know also from the original problem that lambdas have to be greater than or equal to 0. Right? The lambda vector. So that's then this is the dual problem. And you solve the dual problem. And then the other thing to notice is there strong duality? The answer to that is, from the slides, if everything is linear, strong duality is condition holds. So yes, everything is linear. Therefore, there is strong duality. If I solve the dual problem, I get the same Lagrange multipliers as the primal problem, the same result that will give me the solution. The same solution is obtained. It doesn't come for free, right? It's not magic. So you still have to eliminate x as an intermediate step. So it's just a different way of solving the same thing. The solution doesn't appear magically just because you write the dual. To write the dual, you still need to eliminate x. Essentially, you still solve for x and the lambda and the nu and the mu and the Lagrange multipliers. But it's just in a different way, in a dual way. So question 8 and 10 have the same machinery. For different type of questions, you write the dual and find the dual problem. In 8, it's straightforward. It's just more algebra in it. That's why I skipped quite a bit of algebra. And in 8, you also write the dual problem and solve the dual problem. Show that it is strong duality and so on. And the solution is there. Any question on this? So there are, this is the end point of a linear programming course, for example. If you take a linear programming course, they talk about a lot of algorithms to solve linear programs, like simplex algorithm. But simplex algorithm is old school these days. Everything is interior methods, iterative methods that go inside the constraint set and reach the solution. And then there is the duality. You can solve the dual problem. Again, if your constraints are less than the dimension of your decision variables and there is an easy way to write the dual, it's better to write the dual. We will see duality again when? If anyone knows? When we do the support vector machines. As a classifier, when we do the support vector machines, actually support vector machine primal problem is a quadratic problem because it's convex and convex linear constraints. It's a quadratic problem, strong duality holds, and we will write it as dual and solve it in dual. Everyone does it that way because it's easier to do. And it's easier to interpret the dual through the support vector machine. So this has duality has direct implications and direct uses also in machine learning. I think we should give a break. I lost 5-10 minutes in the beginning, unfortunately. And then I will say some last words on optimization. As I say, 8 and 10, I'll leave it to you as an exercise. The solutions are already in LMS. And then I will talk about a little bit of a couple of solution methods for constraint optimization, and then jump into machine learning basics. All right? So let's continue at 15 past. Or should we continue immediately? What's your take? Are you tired? Yes. Let's give a break, yeah. Let's give a break.
Why do you say in this case it's going to be negative infinity?
Because this is, let's say this is 1.
Okay.
I can choose x as minus infinity when I minimize.
All right. So
Let's say this is minus 1.
okay.
Then I can choose x as infinite and make it again
Yes.
minus infinity.
But the thing is, like, why do we discuss like these functions like this? Why we have
Because it's a conditional situation. Either this is 0, where you have this situation, and if it's not 0, then you have this situation. It's a condition.
It's about this one.
Yeah, it's all about that. Because that's the only one that affects x. There is no x here.
Yes.
Yeah, that's a bit tricky, but yeah, all of the duals are like that. For certain parameter sets, it becomes, you get a minus infinity result when you minimize to find the x. So you need to be careful. And this condition gives you the equality constraints of the dual problem. So in that sense, it's also important.
So we talk about the part that.
So this is imposed to the dual problem, right?
So we're going to talk about the part that will affect the x, like which is the one we want to minimize in the beginning.
Yeah.
But why look at if shall we write it like
It's the same thing. Yeah. It is like when you have a matrix multiplication, A times B, right?
right?
So if you take it will give you a vector. C, so this is this, so you have this, this, right?
Right.
If you take the transpose, then it will be B transpose A transpose equals C transpose, which is this A transpose and equals this. And it's the same thing when you do the transpose here, otherwise this is going like this. And this has to be like this. I should have done it the other way because you're doing the. Yeah. I should have done this one this way. Because you do this multiplication by row, right? And then this will be done this, and then this becomes column by column. This transpose gives you this one. Each of them will be one element.
So I think I recognize there's one mistake, like you missed the transpose sign here for this one. In your notes. So
Thank you. Let's correct that.
it's here.
Thank
Yeah,
you.
and
Thanks.
so you said that this is actually the same as this condition, right?
Yes,
It's just
it's just a transpose.
transpose.
Yeah.
okay. But
And
like,
then you need to be careful with the.
yeah, but like, why don't you transpose
C
C1.
should,
C1.
should be
Yeah.
like this.
This should be all contrast.
Yeah, then it's
That
consistent.
makes sense.
All right. Yeah, you need to be careful with what is
Yeah.
row and column and so on. Yeah.
Yeah.
Good point.
I'm interested in why is there no constraints on mu?
Because it's equality constraints. Lagrange multiplier of the equalities.
So mu is
Lagrange multiplier of the equalities have no conditions on it.
wait, so mu is the equality constraint.
Yeah, mu, yeah. Ax equals b gets the nu. It is from the Lagrange multiplier, right? This is associated with the equality constraints.
Oh, okay, yeah.
Then there is no, it can be anything.
I just got like confused.
It's alright. It's new, of course. Yeah. We're just learning.
I think some points we had lambda was the equality and mu was the.
Yeah. This question was, the answer was that I just followed the answer.
It's okay, it's good practice in adaptive.
Yeah. Yep.
Professor, can I have a question about the duality, the weak duality? Since
The
I
equality
know-
always holds. You get a result that is less than.
yes,
the
I
minimum.
know that this is always smaller than
Yeah, that's what I say here. Yeah.
yes, but how can I understand this graphic?
Yeah, let's not go there. Because this is there is a long story behind the graphics there. So I just wanted to visualize it.
Okay, so
You can read the Boyd's book, the relevant chapter. There's a long story about the whole graphical interpretation. It's really long.
so what we should understand is just
Yeah. And I wanted to show it graphically. Like
surely, sorry.
show it graphically that it is below that.
Yes, but why did that?
Yeah, just check Boyd's book. Read the Boyd's book, and then if you don't understand, you can come back.
Okay, thank you.
There's that duality discussion there, lengthy story about
So the chapter 5 or chapter
whatever chapter is duality. Yeah. We should start. We should start. Yeah. All right. Let's conclude the optimization discussion. I have additional things to say, and then we will go to machine learning. So things are not perfectly aligned, I know, but in terms of workshops. But as I was saying, you will have time to finish your machine learning workshop quite a bit. Okay. Any questions before we start this part? No? All right. There are multiple solution methods for constraint optimization. The couple of them that I wanted to talk about mainly, and I'm skipping the projection methods, just I will mention them, maybe next year I'll put a slide on them. This is, I think, important, the penalty function method. It's quite important conceptually, and it also touches the multi-objective optimization. So let's say we have an optimization problem with a constraint, and the problem is actually this has been maybe I should use the pen here. So let's say this is S. So let's say the constraint is x is less than or equal to a and b, right? So in this case, the constraint will be x, the scalar problem, right? In general, though, let's say we have a general optimization problem, and the x belongs to some constraint set, which can be defined through various means, like it could be inequality constraints, equality constraints, and all that, right? We can actually solve the problem as an unconstrained optimization problem by adding a penalty function. And penalty function should impose these constraints. What I mean by that is graphically, let's look at in one-dimensional case. So let's say my constraint is simply, I want to minimize f of x, and x is less than or equal to, between a and b in that interval. Can I devise a penalty function that the objective goes very high when I'm trying to minimize the cost goes very high when I'm outside the constraints? Yes, I can do that. For example, I can add a p of x with some constant c and choose c very large if necessary. But I'm just plotting cpx here. I can add this to the objective function and choose this p of x penalty function carefully to impose the constraints. So if this is the constraint set, then I can make it, for example, for c equals 1, I can impose this penalty function. So if I'm outside the constraint set, I get penalized. And I can choose c very large so that, I'm kind of creating a penalty barrier outside to the boundaries of my constraint set. That means if x is greater than b, then the objective function will be very large. That means the optimizer will avoid that. It's not perfect. No matter how much large you choose c, you may violate the strict constraint, but you will get penalized harshly, right? Therefore, I'm actually, in a roundabout way, imposing the constraint to the problem. But the advantage is, though, I've turned my constraint optimization problem to an unconstrained optimization problem by doing this modification to the objective. Make sense? So let's say I'm trying to climb a mountain, and then there is a barrier that will be the hard constraint in the constraint set. Instead of the barrier, I put a lot of additional rocks on top of it. So theoretically, I can climb it. There is no barrier anymore, but it will be very difficult for me to climb. So it's a bit like that penalty function that you add to the objective function is representing the constraints. So let's look at the formality. If c needs to be a positive constant if you are minimizing, so I need to make it more difficult. And if you are maximizing, that needs to be negative. And p is a function satisfying, p is continuous, p is greater than or equal to 0, and then p is 0 if and only if you are inside the constraint set, and p is very large if you are outside the constraint set. So that's the what you see here, right, with the penalty. Okay. Let me actually maybe show it a bit more like in the notes section. For a single constraint, then it will be like this. So you have let's say penalty method, right? The method. So let's say I want to minimize x squared subject to x is greater than or equal to 2. Yep, that should work, right? Then let's just draw this. So we have 0, 1, 2. So this will be x. This will be then f of x. And then it's quadratic, right? Yep. So obviously the hard constraint version will be like this. So the result is 4, right? But I can actually turn this to a penalty function method by introducing a penalty function at 2 that goes up very much. Right. So, for example, I can define an f of x. I'm just making up on the go, by the way. F of x is 0 if x is greater than or equal to 2, because it should be, the penalty function. This is the penalty function. Let's call it p of x. So I should call this p of x. Maybe use the blue. All right. I don't want to penalize anything inside the constraint set, but I want to make it very large. Like let's say e to the something. No, maybe let's make it some polynomial x minus 2 to the c times x minus 2 to the squared. Then this would be like that, but this only when x is less than or equal to 0, less than or equal to 2, less than 2. Right? All right. So you see, if I add this to the penalty, so this would be the constraint optimization. Right? Optimization problem. Then I get with the penalty function method equivalent but approximation. I should be able to write hopefully one day equivalent approximate. It is approximate optimization problem because it's not perfectly imposing it. Would be then mean x. By the way, I keep saying it, but I forgot myself. What would it be? X squared plus c times p of x, right? And in that case, how does this thing look like? It will look like around 2. So it will look like this plus, plus this function. Wow, this is very colorful. So like this is imposed. Oh, all right. Okay, then this side, this side is actually not terribly important, x squared, but then it is, it's even higher because of this is this. So x squared needs to be added, so the real one will be like this, right? So this will be then the joint function, something like that. And when you minimize, you see you will be around, it's an unconstrained one now. Right? So this will be then x star is roughly the same x star as before. Right? That will be then this. Makes sense? I can always put barriers, penalties to replace the hard barriers. So then it's actually a soft constraint when you move it to the objective function. Okay, I see. Yeah, it's very intuitively nothing. Actually, this is also, I would like to say a couple of sentences about the also multi-objective optimization, because this is quite relevant to multi-objective optimization. So let's say this is something to keep it in mind conceptually. You may have multiple objectives, right? So you may have actually some, until now we had an f of x, but you can have mean x, f of x plus g of x, let's say I want to minimize not only f, but also g. So if I have two objectives, f of x, g of x, then let's say I have the ax less than or equal to b. Right? Constraint is the constraint. So actually, I can, what am I going to do then? I have two objectives. Sometimes you can maximize both of them at the same time. That's called the Pareto optimum. But often you cannot. You need to trade off things. So then, how am I going to deal with two objectives? The answer is very simple. You just combine them. There is one way of doing it is you just say it's alpha times f of x, f, and then beta times g of x, and alpha, beta are scalars, and I'm going to just combine maximize a combination of them, right? Subject to ax less than or equal to b. You see, this is very much like what we have been doing. So you can actually, then you can do multiple things. So you can actually move things to constraints, make them hard constraints, move things to make, and you can, just like you have taken the constraints and make them soft constraints and part of the objective function. So you can actually take this and create variants of this. Like I can do, for example, minimize f of x subject to, I want maybe g of x greater than or equal to some k, right? Or less than or equal to some k. I can impose some condition like that in addition to, it's not the exact same thing, but maybe I'm imposing that condition that, I'm trying to minimize g of x, but all I'm saying is, okay, maybe I will not be able to get it, but as long as g of x is less than k, I'm happy. So that's one variant. Or I can actually take, I can do the flip side of it with the g and say f of x is less than or equal to L. Or I can put everything to the objective, mean x and alpha f of x plus beta g of x plus penalty, c times penalty of x, which penalty imposes ax less than or equal to b. I choose p in such a way that it imposes that ax less than or equal to p, just like we did. You can do it in also multiple ways. So you see, like, when you look at the whole constraint optimization, which is also touching the multi-objective optimization, the most standard way is you just do a weighted sum of the objectives and put them to the objective function. Then we are in the same situation. But there is this trick that you should kind of know in the back of the head, and this is very useful to know. That's why I'm kind of making a parenthesis here. You can take, just like we did, penalty method takes the constraints and puts them to the objective function, makes hard out of hard constraints soft constraints by defining a carefully designed penalty function. And likewise, if you have a multi-objective problem, you can take some of the objectives and put them as hard constraints. You don't get the same thing, of course, but then you are imposing some type of a quality of service constraint. One of the objectives, you say, I'm not going to minimize it, but at least it should be less than something. And then you can turn some of the objectives to hard constraints like that too, if you don't need the really minimum, but less than certain amount of something. And then create different versions of the same story. They don't exactly match, but they are in the neighborhood of the same thing. And yeah, I just wanted to give this as a food for thought at a conceptual level. We will not solve any problem on that. Maybe next year I'll put some slides, but don't think they are different things. So any constraint you see can be put to the objective through penalty function. Any objective to see can be put as a constraint if you are just after certain level of performance for that constraint instead of finding the bottom of it. Make sense? Little bit? At least you have heard of it. That's also something, instead of not having heard of it. Let's do an example with the objective and the penalty method. And then that's one of the last things we will do on the optimization part. So that's the question 11. So we can actually make this a bit bigger. Yep. So let's look at the problem. Minimizing f0 of x, which is convex and differentiable nice, and we have a bunch of equality constraints. All right? we have actually this simple idea. Equality constraints means I need to put a penalty penalizing any deviation from the equality. A classic way is writing it like this. You write a cost ax minus b and then norm square. That means essentially ax, so what this means is ax, sorry about that, ax minus b norm square will be then sum over I, ax ith element minus bi, right, squared. Yeah, norm 2 square is this, basically. So you see, you are any deviation of the element from equal to b, you are penalizing, and you can put a nice alpha or c in front of it. Any deviation, you multiply it with 1 million. So that means any deviation I penalize very harshly. So I create a penalty function around ax equals to b, right? So that is another way of imposing it. Therefore, with the penalty function approach, I turn this constraint optimization problem, or approximate it, by this original objective function and then this penalty function, which imposes the constraints. You got this, right? So this is there is nothing mysterious here. Just I'm writing a penalty function that penalizes any deviation from the constraints here. So the question asks then the penalty term. This is called the penalty term for this additional term that I'm adding. So I'm essentially, through the penalty function, penalty method, I'm bringing that hard constraint to the objective as a soft constraint. It's called a soft constraint because now I can violate it. When you write it as a constraint optimization, it is impossible to violate it, right, mathematically. Now I can go epsilon further because depending on how big alpha I choose, I can still go out a little bit. You know, the wall is not a hard wall anymore. It's a pile of rock replacing the wall, so I can go a little bit. So the idea is that the minimizer of the auxiliary function, this penalty function, should also be an approximate solution of the original problem, as I said. The intuition is that the larger the penalty weight, the better the approximation. That also makes sense. The steeper the pile of rocks, the better it approximates the hard wall, right? Therefore, this terminology, hard constraint, soft constraint, is also nice. So soft constraint means I can go push it a little bit, like it's like jelly, whereas the hard constraint is a wall. I cannot push it anymore. And then suppose x tilde is a minimizer of the phi. This is a minimization problem. Show how to find x tilde a dual feasible point how to find from x tilde a dual feasible point for this. So actually, I can write also the dual of the original optimization problem, and then find the corresponding lower bound on the optimal value of the original problem. So it is kind of creating a connection between the dual and the penalty method. So let's have a look. So if we write it, if x tilde minimizes phi, then taking the first order derivative, this is an unconstrained problem. I just assume it is convex, and then quadratic is also convex. So convex plus convex is convex. So it's a convex optimization, unconstrained optimizations problem. So essentially, I'm doing min x tilde element of R and then phi of x. Right? That's the unconstrained case. So I write the first order conditions. That will be then f0 of x, x tilde with respect to x tilde, plus if I take the derivative, it will be 2 times alpha, right? And then the individual xi's, and then that actually, if you write it in the matrix form, back in the matrix form, we get the ax tilde b. Times, I've also the a here, then I need to take the derivative with respect to ax tilde, and then that brings actually here and A transpose. 2 alpha A transpose. And then the original. So 2 times alpha, this, and then inside, when you take the derivative, it brings and back right in the matrix form. X is on the other side, therefore you get an A transpose X. This comes from, let's make now note, gradient of X, AX is A transpose. Yeah? That's because of that. You can check it. All right, so this is equal to 0, necessary condition, right? And what I can do is actually if I write this as such, right, so that if I look at also the Lagrangian of the original problem, then the Lagrangian will be f0 of x plus mu ax minus b, right? And if I take this, as the Lagrangian, take the Lagrangian's derivative with respect to x, I get also f0 plus A transpose V VA, right? So if I take the, no, VA transpose, right? This is. Yep, that's a dot product.
I think the derivative is not right about the derivative of the norm of ax minus b. It should be A transpose times A plus A times A transpose.
No, I think this is correct. So let's sorry.
The derivative of the norm is not that one. It's not 2 times alpha AT AX.
I think this is correct. So let's leave it at let's take it offline. All right. So we can discuss this offline. So this is actually I pretty much am sure that this is correct. So and if it's not, I'm going to correct it. It's maybe a transpose here and there is not the main issue here. So when we take the derivative, and then we get this, and I write the Lagrangian of the original problem and take the derivative, then we get this, right? And then when you compare the two, actually, if this is 2 alpha ax tilde minus b, then you get the same result. But then this is the same as this, right? So this is also equal to 0. So there's equality here if if I choose mu as this. Okay? So once I do this, by the way, I can write it as also from the Lagrangian I can write the dual. Now I can write from Lagrangian of the original function of the primal, which is this L. I can write the dual function, which is g of mu, and that's mean x, f0 of x, and then plus the ax minus b. So this is the same Lagrangian that I need to minimize, right, to find the dual function as we have discussed. And when we do that, actually, we see that if you substitute actually the v here to here, the dual function becomes f0 of x tilde plus the v I substituted here, so I get 2 alpha ax tilde minus b. There is another ax b here, so they multiply, so you get the square, which I can write also ax minus b squared, right? And then I have this dual. Notice that is the same as the quadratic method, the penalty, with some factor 2 alpha here. So I'm actually, when I do the penalty method, there is a kind of a nice connection here. So if I take the original problem and write the dual, and if I choose the Lagrange multiplier in a certain way, then I end up with the dual of the primal problem. So I established that connection for a certain choice of the Lagrangian multiplier. And because of this choice, we also know that the original problem, f0 of x, because of the weak duality, I haven't established the strong duality here, has to be greater than equal to it has to be greater than the maximum of the dual. Therefore, it is actually greater than f of x tilde plus 2 alpha, as we have done, x tilde minus b squared. This is for all x for all x such that they are on the constraint set. Right? So this is from weak duality, which always holds. So in that sense, the problem is nice. So you find the lower bound on the optimal value of x, objective function. So for all x star, so this is then this is the solution minimum of the primal problem is greater than the maximum of the dual problem. And then there is this nice connection to the penalty method as well if you choose the Lagrange multiplier in a certain way. In this sense, the problem is quite nice connecting a few things together. All right. So I kind of today is almost gone with the. I've skipped this one, 12. I skipped. It's a very nice geometric problem, but I leave it as an exercise to you, and it's a bit advanced. And the last thing I want to say is the active set methods. There is also the projection methods, and again I'm skipping them a little bit. The reason I skip the projection methods, gradient projection methods, is when you do the gradient algorithm with constraint, you may need to put the gradient direction pointing inside the constraint or towards the constraint, taking into account. They are not that popular anymore. At some point they were the state of the art. These days you do the interior methods. They are more like a gradient descent, iterative gradient methods that everyone uses, so that we have learned. The other methods are a bit just you take the gradient and take into account the constraints and do a projection. There's a geometric projection that can be done. So I kind of skipped that. Maybe next year I'll mention it a bit more. But more important method is the active set method. Penalty methods are important. Active set methods are also very important and actively used quite a bit. So the idea here is very simple. So you take the constraint optimization problem, and we said that if you have equality constraints, they are always active. So there is nothing to discuss there. But if you have inequality constraints, they may or may not be active, right? And you may have a bunch of inequality constraints in many of objective problems. You can write the KKTs here, right? This is the KKTs. What we do is find the set of active constraints using an iterative process. You don't know, when you start, you don't know which constraints will be active which inequality constraints will be active at the solution, right? So you may go from inside, you may go through the boundaries, but when you find the optimal solution, some inequality constraints will be active, some of them will not be active, which means some of them will be less than 0 and they will not play a role, right? And in the beginning, you don't know it. If you take all of them into account, that's computationally very expensive. So what the clever method says, you know what, I'm going to start from an infeasible point and repeat until optimal enough. I will choose some initial set of active constraints and treat them as equality constraints. And then solve the problem with those as the equality constraints. Find the Lagrange multipliers. And if the Lagrange multiplier is negative, that tells me, oh, this constraint shouldn't have been active. And then I remove it from my set. And if I hit other, and then I search for the infeasible constraints, then I look at my first iteration solution and check the constraints. Oh, if I violate some of them, some of the ones that I haven't included in the set, then that tells me, oh, these constraints are active. I should include in my current set A. So I change this. I keep a track of an active set, an estimation active set estimate, and doing this iteratively, I solve the problem, then look at which constraints are really not active, then I look at which constraints were active but I didn't take them into account. I add and subtract iteratively, essentially, change this set until I find the solution. So this, as you can imagine, makes the problem easier, computationally, because instead of taking into account maybe 100 constraints, inequality constraints, I start with 10 inequality constraints. Solve it for 10 times easier than check, out of this 10, were there any that have negative Lagrange multipliers? Then I shouldn't have taken those into account, remove them. Maybe I end up with 8. Then I look at the other 90. At my current solution, which of those 90 are active? I include them in my set. Resolve it, redo it, and then it's kind of a combinatorially complex thing, because you can have as many large number of subsets, right? With 100 constraints, we don't know how many. Let's say 10 of them are the real active. It's 110 combinatorial. It's a very large number. So you get an approximate solution, or it's a long iterative process. Therefore, you repeat until optimal enough, or your time runs out. And then this is the whole idea of active set method. So you kind of add, subtract, add, subtract. Maybe next year I'll put it to the workshop, but for now I didn't. You can try if you want at all, with your now current knowledge. So this shows constraints to be dropped because you don't need. For example, this case, I'm hitting this constraint. This constraint doesn't play a role. I drop it from my set, or constraint to be added. So I start here, come here. You see, I hit here. Suddenly, this constraint needs to play a role because I cannot go here. I need to go here. So this is now added to my set. This is added to my set. This is subtracted. This one is subtracted from my set visually. And then I do this all the time. The Lagrange multipliers tell me if they are positive, then they tell me, oh, that constraint is active. If it's negative, then this constraint shouldn't have been there. Kind of I remove it. Yeah. All right. So that's the last word for this stuff. Any questions? Yes. Yeah, but you put the inequality constraint as an equality constraint. So you treat it as an equality constraint artificially. And because it's an equality constraint, it can be positive or negative. Yeah. So that's a very good question. But it is doing something it's not supposed to do, because you included it as an equality constraint, and then it shouldn't have played a role. It's kind of a direction, right? You included an inequality constraint as an equality constraint, and it wasn't playing a role. That means you artificially impose that equality constraint. The Lagrange multipliers negativity tells you, the correct direction is that way. And that tells you, oh, okay, I did this a bit artificially. Right? There's that interesting interpretation. I think less than or equal to 0. Zeros are also, zeros are also not, those are not active, yeah. Yep, it's a very good question, thanks for that. All right, we covered too many things. Just exercise a little bit. with the questions, and check the books especially. There are also examples in the books, and just try to get the main idea. I'm not going to ask deep questions, very complicated questions in the mid-semester test. I will just check whether you understood anything or am I talking to myself. So expect some basic understanding questions in the MST. I will send an email regarding that. I would like to at least start with the machine learning, because starting is half of finishing, they say, right? So at least we start with 2 minutes with the basics. I will cover some of the basics and what is data and what are the learning tasks. Then I will go to linear regression, and I'm going to use linear regression to illustrate the concept of overfitting, and then little bit also regularization to prevent overfitting, right? I'm kind of making that choice. Of course, overfitting happens everywhere, but I'm using linear regression to illustrate it. Then I will do some basic Bayesian decision theory, maximum likelihood and MAP, because they're also built into the whole deep learning as well. And then, yeah, as I said, maximum likelihood and maximum a posteriori. And that concludes the basics. The next step is I have a slide set on unsupervised learning, at least a flavor of it. And then I have another set on afterwards on supervised learning, or a flavor of it. Then I will go to neural networks, bit deep learning stuff, and hopefully finish the end of the semester with a little bit of taste of reinforcement learning, right? So it's a potpourri of a lot of things that hopefully you will get the basic ideas. That's my goal. I see myself succeeded when you get some basic ideas of these important topics, and then I fail if you don't understand anything out of anything. So then that's also, as a partner in the crime. So the reading suggestions are here, so you're supposed to have a look. Machine learning basics, most of them are chapter 1s, pleasurable reading if you wish. And okay, so just the last words. I want to conclude with a bad joke the day, and then we see each other tomorrow. It's all about data. Machine learning is all about data, right? It's different from the engineering education probably that you have taken. We have a very heavy program with a heavy focus on modeling, and that's good. Nothing wrong with that. But the whole story with this machine learning, deep learning, all that jazz is it's all about data. And then the bad joke is there. Does anyone know Star Trek? So this is the Commander Data, right? So with my apologies. So a bit more on the serious side. During the 20th century, you should realize also a little bit, you should know some history, right? History is important. Data was hard to obtain first. Sensors were very difficult. I had a friend 10 years ago, installing an operating system on the sensor itself was a multi-week task. Now you buy them and put an SD card and it works. It was expensive to store. Storage was very expensive. And then it was expensive to process because computer CPUs were expensive, right? So this was the 20th century. What we have now is we have tons of data. You can put tons of sensors on the cheap side. They generate enormous amount of real-time data. Then you can analyze afterwards. It's cheap to store. You have terabytes of storage. And then it's cheap to process. We have, supercomputers in the pocket. So are we taking advantage of it? In my opinion, in engineering, not enough. And that's the whole thing is about. The whole subject is about this. And I think you are here for that. And this is a very nice sentence. We are drowning in information and starving for knowledge. Right? The guy is summarizing. My saying is, information is free, but knowledge is priceless. You can find any definition online on Wikipedia, but making sense out of it is difficult. Right? The knowledge is priceless. So that's what I'm trying to empower you with, is some knowledge. So when you go read some stuff, you can make sense out of it because you know the basics, hopefully. Right? So we will continue tomorrow, and then I will go over the really basic ideas of machine learning, and then, yeah, that's the rest of the program. See you tomorrow. Expect some emails from me in LMS.
would like to have a suggestion for the workshop.
Oh, okay.